I know it's a seminar with high performance, focus on high performance. I want to talk a bit about some topics that I think directly go into this direction, but are not yet on an overly large scale, admittedly. But nonetheless, I think it's a really interesting and exciting subfield of machine learning and AI at the moment. Right, you could summarize it as this generative AI, and I should mention I did get help from Sora and Co for these illustrations. You see the dramatic background, but it fits the topic, right? So we're trying to actually use similar techniques for simulations, and also a couple of the images here come from that. And the main question is, right, how do we actually use these techniques for physics simulation, like solving PDs? All right. I do want to start a bit more general, and right, this is sort of interpretation of the challenges of humanity. So we have quite a few, I think, and we need all the tools we have to address these challenges. So I used to find it very necessary to motivate why looking at deep learning, AI, machine learning, neural networks, and so on. Now with the Nobel Prize, the Thürey Awards, and so on, I think it's clear that there is something interesting. It's definitely a powerful technology. Nonetheless, many open questions, but I think it's right. I need to do much less work on defending this combination at all. So in the context of this generative learning, one of the key drawbacks in a way of traditional simulations are that they're deterministic. You could argue that's an advantage. That's how it should be, right? We have a computer. We need to rely on an input providing a certain output, right? If we look beyond scheduling of multiple processes, for example, but generally we have a deterministic system, deterministic simulator that gives one input, produces one output. The challenge here a bit is that the nature around us is very complicated. We have ambiguities, we have uncertainties. We have effects like the butterfly effect illustrated here, where we're dealing with systems that we do understand. We can predict how they evolve, but a tiny change in initial conditions can lead to very large changes later on. So it's predictable, right? It's not complete chaos, but right, very small changes and potentially also very small ambiguities in initial conditions in our setup of a simulation could lead to very large outcomes in terms of the end result. And right, if you think about stuff like weather, this is actually a very good example where tiny changes and uncertainties about tiny changes could have a huge impact, leading to maybe a hurricane being detected or not. And there are definitely important and challenging questions in that area. So the main topic now here is how can we deal with these uncertainties? And I think these generative modeling techniques are actually nice technology here. And what can we do with these beyond chatbots? Also, I do have a disclaimer here. It's worth putting on the slides. These AI techniques here, I think, really should help to improve our simulations on all fronts. It's not just making them a bit faster or a bit easier to use or so, but they're really interesting capabilities, especially on this side of dealing with uncertainties that I think go beyond what we can do with traditional techniques. I do want to show one of the motivating examples from our lab. So we have a small setup here. This is in one of our Besenkammern or cupboard rooms. So we have a small setup of several cameras here, and then a fog machine, and it's connected, so we can control where heat this up and eject some smoke, and then film it with these cameras. It's in a way very simple. There's a tiny puff of fog that comes out here. It's a hot diffuse oil, right? So in a way, very simple thing, but nonetheless, reconstructing the motion of the air for a thing as simple as this little puff of fog is actually very challenging. So we can see it here a bit. I mean, we see something. Obviously, we can assume we have a good intuition for how the air rises here. But this is transparent, so we have potentially multiple layers moving against each other. We actually don't know the initial conditions. There's a lot of uncertainty here. We cannot, this would be super difficult to do anyway, volumetrically capture the initial state of our system, and then predicting, this is not even a very high Reynolds number also in terms of flow, but predicting how this flow evolves is a really challenging and very strongly underdetermined topic. So that is actually a good one to target with techniques like I will talk about in the following. And you can generally summarize this. reconstructing natural phenomena like this one from ambiguous and sparse measurements. And right, I think there's a direct link to things like weather and climate, right? Weather, we can't globally instantly capture a full state, but we have very sparse and spot-wise measurements. So I think it's in a way a nice analogy. Yeah, talk about Gen AI. So generative modeling for AI techniques is in a way a surprisingly simple task. So we're dealing with mapping distributions. We have uncertainty, we have a probability distribution. So probabilities will come up several times in my talk. I'll mostly skip equations. I want to more explain the larger picture here, but the main idea is really we have a target distribution, right, as shown here. Could be anything, any probability, certain events along X have a certain have different probabilities, and you can see there's a peak here. Right, this is the most likely event, basically, but it's spread out. There are two of these peaks, and if you would sum over all of these, you get a mean that's probably slightly shifted, so would not even capture this one peak. So, right, just to give some example of something that's a bit more complicated, and we somehow want to capture the spread of these events, in this case, just along one single variable. And the way to do this in machine learning is typically that we start with a distribution that we can deal with. So this could be anything. We don't have a handle on this. We could start with something simple. It could be uniform or a Gaussian distribution. Gaussian actually turns out to be a better choice for most. And then the main question is, how can we map from this simple distribution that we have under control to this complicated unknown target distribution? And that's really a fundamental question behind all of these generative tasks in machine learning. It's really an old problem. So this is very old, since the very beginnings of machine learning. The only thing now that changed is that with these neural network techniques, we actually have pretty good grip on this for high-dimensional ones. So later on, right, if you think about the flow of volumetric state, it's not just one variable, but potentially hundreds of thousands or millions of degrees of freedom that have a joint distribution. So we don't just want one of these values to have the right values, but they all need to go together and form consistent and realistic states that vary with the right probability in the end. So the breakthrough in my group is the following, and I have this picture here to show you a bit. It's about an airfoil, so you have cut through a plane, just a 2D case. For flows is as simple as it gets, really. A steady state flow around one of these sections of an airfoil. And here we're looking at single geometry, just varying Reynolds numbers across X here. So for those of you know, right, basically lower Reynolds numbers towards the left are more laminar, basically boring flows where not so much is happening. And towards the right, we have more and more turbulent flows. This is with a simple turbulence model. So the Reynolds numbers get very high in the millions here, but average over time. What happens on this side that we have more and more variance, and even steady state solve in this case actually produces different answers depending on what you provide. So on this side, we actually do get different outcomes for the simulator. On the left side, not so much happens. It's very steady, and we tend to go towards a single solution. And this is now what we tried capturing here with different methods. And this is the key result for our group. It doesn't look so exciting at first, but let me explain what happens here. So we have a ground truth here. Because it's a simulation and not an overly expensive one, we can really broadly sample each of these different flow regimes and establish how they vary. So what's shown here is along Y, the standard deviation. So just in terms of standard distribution, how much spread you have in the answers. I'll show some examples. They're not just a Gaussian in the end, but nonetheless, it's a good measure of how different the solutions are. And the black one is the ground truth. So larger Reynolds numbers mean the outcomes vary more. So this is what we like to capture. There is a model here, the blue curve, that does it surprisingly well, but this is actually directly imposing this Gaussian distribution as knowledge into what we fit. So it captures the standard distribution, but I can show in a moment, in the next slide, this doesn't do much else. So it captures the spread, but we actually cannot get a state out of this. There's another deep learning variant here that used to be very popular a few years ago, but by now it's already out of fashion. These Bayesian neural networks, these try to capture this and seem promising at the time, but what you can also see here is there are three curves that depend on one of the hyperparameters for learning. And that means we have to, this parameter you have to specify beforehand. So depending on what you put in, you get a different spread out of the solutions. And even worse, they actually don't vary. The spreads are pretty much uniform. So no matter what you input, the model just learns depending on what you put in to produce certain variance in the output. So this is unfortunately completely unusable, right? We put something in, you get an output, but it's not even adapting to the data. So this unfortunately did not work. And what turned out to work are these diffusion models, what's driving all the Gen AI topics. That's the red curve here. This actually now has almost no hyperparameters. So you really just give it the data, and from the data, it learns that for low Reynolds number, right, the solutions are consistent and don't vary a lot. And for larger Reynolds numbers, that there's more spread. I should mention here, you might see the light gray areas. Those are actually extrapolations. So this was not in the training data. It's already interesting to point out. So here, for example, it does remain rather flat. So it does not cover this trend in the distributions to extrapolate, but at least it doesn't go crazy. Also on the lower end here, it overshoots because it mostly keeps what it saw in the training data. So not perfect here, definitely, but also it could be worse. It could do arbitrary things in the not seen region. Yeah, but overall, also this was basically one of the first algorithms that really just from the data captures this distribution. And these are the actual thing that were learned here, just to provide some examples. So it's a tiny resolution, 32 by 32. The light white area you see here, this is the airfoil, then the flow around it. And for one of the larger Reynolds numbers, these are the different possible solutions you get and that were in the data set. And now these first two methods, Scholastic and the Bayesian neural networks, provide mostly noisy solutions. I mean, they capture the airfoil a bit. This is provided to the network initially, but around it, well, okay. Also, roughly you can see low and high pressure here in terms of the colors, but not much else. And this diffusion model now produces for one run an answer like this. I'll come to it in a moment. We're dealing with probabilities, right? And in this case, it actually does produce these different samples if you run it multiple times. So in this case, you cannot control what you get out exactly. It is a distribution we're dealing with. But if you provide with different random seeds initially, you get different answers, and they actually do capture the probabilities of these solutions in the training data. In this case, it's actually very similar to the second example here at the top. So yeah, this is a good indicator. And also if you compare it now on a similar level of accuracy, so fair comparison, or at least as fair as it gets in this context here, it's actually also faster than in this case, the open form generator for the data. I do want to quickly explain what's behind this, how this diffusion process works for those of you that haven't seen it before. It is a bit of an unusual setting for machine learning. So what we're dealing with is we have a data set sample here on the left-hand side. This is one of these airfoils now in high resolution. And as a first step, we actually destroy this. We remove all signal from here and turn it into pure noise. There's really nothing left here. This is pure noise. And then we want to learn the reverse. So now we want to go from this pure noise that has no information, basically, back to one of these samples. So it seems unintuitive at first, right? Why do we go through this process of destroying the data? The nice thing, it turns out this is a stepwise process. So we can control how much noise is added in each of these steps. So it's gradual. And we know how the noise changes. So this is something that we can later on use to determine how much noise should be removed in each step. But also, I hope it's what comes clear here is that this is a stepwise process. It adds basically another dimension. So it's more expensive. Also, the normal neural network or so would go and produce an answer like this in one step. And now we have this process of removing the noise in multiple steps. So I'll come to this. In the very first version, to learn this, we're happy that it worked at all and used 1,000 steps. So it's basically 1,000 calls to a neural network. So each of them is fairly fast, but nonetheless 1,000 times slower than a normal network to produce this answer. By now we have methods to get this down, but nonetheless it is more expensive than a normal learning approach. Yeah, one thing to mention in this context dealing with probabilities is that actually I would argue that pretty much all problems that we encounter in science, actually probably also many around, you could see as a conditional probability problem. What I mean by that is that given some condition, some input x, it could be parameter or an observation or so, we want to know the probabilities of this y conditioned on this x, and then basically produce samples from this conditional distribution. So the probability of this y conditioned on x. And in this context before, could, for example, be we'd like to know the probability of these average flow states given a Reynolds number and a certain angle of attack for the inflow. Or you could go to more complicated conditions that you might want to know about the probability of stall events given flow conditions, flight conditions for an airplane or so. Or this could even be you want to know the probability of a hurricane happening here given certain weather measurements. Each of these are basically you could phrase as similar questions, and any normal simulation that you run could be phrased as given the state provided the inputs to your simulator. Normal deterministic simulators would probably give you mean or one of these instances. Here the goal is we want to have all of the possible solutions with the right probabilities. So we also want to know extremes with low probabilities. We want to know the more likely average ones, but we really want to have the whole spread of these answers. Yeah, so we want to get this y conditioned on x that I had before, and I do have to mention Bayes here. I'm sure you all heard of it. So Bayes' theorem is really the foundational equation here to deal with conditional probabilities. In the end, it just allows you to convert one into the other. But this conditional sampling problem, also machine learning, has always been motivated by Bayes' equation here. And what we have here is worth looking at briefly, at least. So we have this conditional probability of y conditioned on x. And in Bayes' equation, this is computed from the kind of reverse probabilities. So you're looking at x conditioned on y times the probability of y. This one is actually typically called the likelihood. And then there's a term that basically is the probability of x that comes from the other side. You typically divide by this down here. That's what's called the evidence, which in practice, in this setup, is actually computed typically as a marginal. So given samples of y, we just estimate how probable the x were given all the y's that we have in a data set or so. So this is really the fundamental equation behind it. People have tried to estimate certain terms. Likelihood estimation is, for example, own subfield in machine learning. So you can try to tackle these Bayesian estimates piece by piece with the different terms. What we do with diffusion is actually a slightly different approach. We're really going for directly estimating this conditional probability distribution given some starting point, a simple prior distribution for this x. And this is actually an important point. So we just have a network F with some parameters theta here that should give us this conditional probability distribution. And we need to have an easy way to provide these prior distributions for x. That's, for example, a simple Gaussian curve or so that I had before. There are different approaches that actually put a lot of knowledge into producing x to make this simpler. But in the end, it's just shifting the problem. Then we have the problem of estimating this prior distribution for x. So one of the nice things about this diffusion model is really we don't need much to compute this and still get this conditional probability distribution here for the y. And it's surprisingly easy to learn. So we want to have the setup, right? But we also need to actually train this F here. I won't go into detail what this looks like. It could be any neural network, basically. But we need some stable way to train this. And this is now, we also briefly want to explain how this diffusion process works. So now we're looking at this slide from before with the noising and denoising. And to train F, we typically have a learning setup that looks like this. So we have some target, in this case called this y bar. And then basically we try to minimize the output of this F of a neural network towards the y in terms of some loss. That could be just a simple L2 distance. Then we try to minimize this distance given the parameters theta. So we want to find the network parameters that make the output of F as close to these y's as possible. And for the diffusion, this now works very nicely by looking at these steps along the noise. So we have a forward process where we basically take these samples y here, and now we step along this noise, that's the R here, and add more and more of this noise. And with increasing Gaussian noise, you can actually show that you basically have a certain noise schedule hidden behind these alpha values here that you can accumulate, and each accumulation of Gaussian noise is again Gaussian, just with a different strength. So you can, knowing how they should be added, or picking some amount of noise that you add over the course of these different R, you can compute how to turn one of the samples at a step R into the next one, R plus 1. So that's a forward step, more and more noise, where at the end for a large R, capital R or so, there should be nothing left. And for R equals 0, we should just have our Y. And now we want to turn this around. And also there, knowing these noise distributions, we can write this out as an equation. I'll skip the different beta terms. They are somewhat unintuitive here. So you basically get the same idea. We have a sample YR. We want to go to R minus 1, so make the backward step. We want to remove noise. For that, we actually add the contribution of this F. This now should lower the noise by a certain step, just according to this noise time. It's a virtual time. And turns out that if you go through the math, you actually have to re-inject a certain amount of noise again, depending on a parameter that brings in the alpha schedule again. But if you're interested in the details, please look it up. There are basically different parameters here that depend on the accumulated alpha values for these different values of R. The important picture is basically, this is pretty easy to compute, right? You just need the current step, you need the estimate of the network, and some additional noise. It's Gaussian noise. Again, this is easy to produce, and we know the strength, this beta for the epsilon is known. And now we can train, this beta have its factors. Now, this is really a surprisingly simple learning objective, because all we need to do is basically look at the amount of noise that we have in the step. We know all the different values, and we just need to train this F to produce this step in the noise. So we can easily compute this by sampling different epsilon values, different noise values. We know how strong they are. We add this on top of our data, and then we train the network to predict the difference between one of these steps. So it's really as simple as it gets. It's a completely supervised objective in terms of such a distance, noise, network. We put in the R, so the network knows where in this time it is. But we just need to look at one of these steps along the way and repeat this training step until the network has learned to estimate this. So in terms of learning, it's as simple as it gets. And it's really, it might take a while, but this is a very simple and stable objective. And that also actually is probably one of the factors driving the success of these methods. There are other variants before that are very unstable to train and tricky and depend on a lot of hyperparameters to get it to converge. This is really simple to do in the end. But yeah, so here on the slide, I have this note. It actually doesn't matter what F looks like internally. It could be any network architecture that is applicable to your data. You could run this on a graph, on a mesh, or on regular data with a transformer or not, or an unstructured data with a fully connected neural network, just to point this out. All right, yeah, I do want to leave it at that with the algorithm and show some examples in action. So one of the things you can actually target here are different time steps. So this is something that's nice to see over time as an evolution and illustrates a bit the effects of this. So now the learning task is basically one time step. What are the likely outcomes of the next one? This is more strongly conditioned now. If we know the whole state of one of these flows, there's not that much room to vary the next step, basically. And these are now different learned variants. I want to focus on these two here, because this UNet is actually the same one as this diffusion approach. It's identical neural network architectures. It's just that this has a deterministic objective to directly produce the output, the next step in this case. And this version was trained with what I had on the slide before. This now runs, well, actually less, on the order of 100 steps to produce the next output, and starts with noise given the previous time step. So the only difference here is basically what I had on the previous slide. A direct learning of the next step versus a diffusion approach. And the nice thing is that here you can already see this loses the whole structure of this flow. with these shock waves. And at some point, these are quite a few steps, several over 200 steps shown here. But the diffusion model is very stable and keeps the structure of these solutions. And one of the nice side effects that we noticed here is this is basically unconditionally stable. So we ran until 200,000 steps, but it basically doesn't break down, which for neural networks is not a guaranteed thing. If they're not properly trained, then they can actually diverge and give garbage like some of these. So it seems that kind of having this more difficult task of forcing the network to learn these diffusion steps also provides stability over time for producing these different states. Yeah, actually, this task we can also see as one of these conditional probabilities, basically providing distribution for the next state given the previous one.
Question:
yes.
How do we see the actual distribution here? We see one solution that
yes.
could be the correct solution,
yeah.
or not.
Exactly.
So where is the distributedness of the result coming in?
That's a very good question, right? Here, the distribution is tricky to see, and because we have now the distribution in terms of different answers and the evolution over time, this is actually a case that's really difficult to evaluate. We had some metrics that basically depend on statistics in the different outcomes, but capturing the distribution over time, especially for these long horizons, is challenging. So we're actually still working on that to really show that the distributions here are right for these time evolutions. Here, I more want to show that one of the nice side effects of the diffusion is the stability over time. But for a proper evaluation, I would ask you to wait for the next example. There we have more grasp on the different answers that come out.
So is it correct to say that in this particular case, you're just showing the most probable outcome for the next step?
Actually, this is also a diffusion process. It should show the right variation with respect to what was in the training data. In this case, with the shock waves, there's a small obstacle here, this compressible flow. So it does have a lot of ambiguity on the numerical side because it's quite fragile in terms of these shockwave formations. So there are potentially ambiguous solutions, and the network should have learned to reproduce these. But capturing the statistics of these shockwaves and these compressible flows is actually non-trivial for this case, and I cannot write it. We don't have results to really show that it matches on that front. But I would guess that also why the other methods have trouble is that there are ambiguities, and the others try to learn this by averaging, whereas this model basically tried to capture possible realistic answers. But it's difficult to really quantify that this happened here. So if you look at average statistics, it looks good, but this is more of an intuition that I need to give here for this case. But right, I'm pretty sure it did not learn the mean. So this is more what you get out of some of the others.
I have a fundamental questions along this line.
Mm-hmm.
Do you simulate a stationary process or a non-stationary process? Because typically flows, at least for me, are associated with non-stationary.
So the previous example I had,
no, this one
was a stationary one, and this is non-stationary. This is transient. So here, this is the reference outcome. It's really this.
Also, I wonder because then the learn time step, the f function should ideally also depend on I. No?
Sorry, on what?
On I, on the step itself. So for each step, you mimic better non-stationary processes if the function f can depend itself on the time step.
It is here. It is conditioned on. That's the conditioning. Exactly.
But you write down f theta. So okay.
The theta is the learning objective. So that is the learning task determines theta, and now it's trained. F theta is fixed for all of these.
But it should also be dynamic, huh? It should also
theta. No, it's a predictor, right? We basically learn a simulator, but the theta
predict something non-stationary, no?
Exactly. So theta is fixed. The x varies. That's what you see here. We put in
the x varies, but also the function f could vary from time to time. Say if you would have a economic time series, you could have weekend effects and stuff like this. You should model that.
But that would be the conditioning. That would be similar to the x, right? But the dynamics of your system would go into f, right? Here we're learning this compressible flow, and this should only do compressible flow. So theta is fixed here. That captures like the simulator, right? It's like a numerical simulator.
Yeah, we can discuss later.
capturing exactly the process that was used for simulating the data. That's in the F. Then it's fixed, and we do the same time prediction like you would with a numerical time stepper. But in this case,
the weights are encoded.
Exactly. The weights are trained to predict this compressible flow, and only this, right? It cannot do weather or anything else. It's trained just for these compressible time evolutions. But here it actually does the time evolution. So it's a good point. The previous one was Reynolds averaged. This was a steady state solution. This one is transient, so it really resolves the evolution over time. And now I want to go back to something more similar to a steady state distribution, but a more interesting case, and one where it really, where we have a better grasp of what the ground truth distribution is.
For the previous part. So how did you produce this video? Did you do a query for every single time step, and the input is the last time step?
Exactly. It's a normal time. So the simulation was done, right? We give time step I, produce I plus 1.
I understand this probability because it looks quite continuous. I would expect that then things jump, because when I use a diffusion model, I get arbitrary output when I do it several times, kind of. Yeah.
The network learned how to go from one step to the next, right? So there is less freedom. The state is fully determined, but if you run it multiple times, actually, especially over time, you get different answers. It's unfortunately, right, with this time dimension, it's basically 4D problem, right? With 2D plus time plus the distribution. On the web page, we have some examples. If you run this multiple times, you get different answers with the same initial condition.
Okay, but I wonder that over time, you say that the time series looks different for different simulations, for different runs.
Yeah.
But the time to time is, so progressing in time is continuous, so to say. That's one solution. And I would think that from time step to time step, you get jumps, like, oh.
Okay, maybe I don't understand, but it's basically the time step, right? You're going from, there's a fixed delta t, but you advance in time. It's like a simulator, right? You call.
So it knows the time, so to say.
It has learned a fixed time step also. This is not a degree of freedom here.
Okay.
The diffusion time varies, but the output of the network after having denoised all the inputs is just one next state. It's really like a simulator. You put in one state, it gives you the next one. But it's trained for just this physics with this time step. In this case, we had different flow conditions, so the shock waves did vary, but it's just one simulator for this case. All right, another scenario that is more relevant in practice is the following one. So now we look at flow over an airfoil. This is now a 3D case. That's why I think it's interesting. So we have a surface mesh simulated. The data comes from a volumetric simulation, so we have the whole flow around it. What we're interested in is actually the pressure distribution on the wing, right? So it's like a case, are there any extreme events in terms of pressure hit on a part of the airfoil? So pressure spikes. We want to know the distribution of what the pressure does along the whole airfoil without resolving the whole flow around it. And the simulations are shown here. So you can see it's also pretty high Reynolds numbers. It's quite turbulent. But now what we look at with this scenario is we actually don't want to resolve time. We're not so interested in how this evolves over time. We want to have this distribution. What does the pressure on the surface look like? And what are potential extremes and means of these states? And now, interestingly, if you think about how these simulations are created, they do converge to an equilibrium where the flow is turbulent and fully developed. And we start with a synthetic initial condition. Right? So we put in the flow conditions, right, the angle of attack comes from a certain angle. And this is what's shown here over time. So there's a transient stage until this turbulence develops, which is unphysical, basically. This, in a way, has no meaning. We should not and cannot draw any conclusions on the actual behavior from this stage. And for simulations, nonetheless, we need to do this. We don't know what the solution looks like, so we need to start somewhere with these synthetic conditions and wait until we can perturb and until it has developed some flow. But what we're interested in is how this stage here, denoted by Z, develops. And now here we can look at take the same viewpoint and see this as a conditional distribution. We have flow conditions, we have an airfoil geometry, and we'd like to know what are the possible pressure distributions on the surface for these conditions. but we don't resolve them over time. So now that we basically discard this time, we can go back to really a distribution view on the surface, but we like to capture these different answers here, just shown as a sketch. Oh yeah, right. The surface. So it's basically conditioned on Reynolds number and the angle of attack, and the geometry actually also goes in here. This varying the geometry of these 3D wings in this case. So now we're working on the surface, right? Because the volume admittedly would have been too large. That had millions of degrees of freedom. The surface has on the less than 100,000 in this case for the mesh. Now with the GraphNet, and the diffusion process now happens on the surface of the wing. But it's the same idea. We start with noise on the surface, and then we make here on the order of 20 steps to get to one of the pressure distributions on the wing. So here now, again, this being we did invest quite some computation resources. These simulations take several hours to produce one sample. This did take quite some time, but we have it under control, so we can provide a ground truth distribution here. And this is now what's shown and compared here in a bit more detail. So here we have what's shown is actually, again, just a standard deviation. So you can see here for this, again, just one sample, but you can see different outcomes for this one geometry. And also just for comparison, this is Gaussian mixture model, one of the kind of more classic ways to deal with these higher dimensional distributions, which in this case did fine for the smaller problems, but did not converge in this larger setting. These two here at the bottom are variants of diffusion models. The main difference now is between these, the L here indicates that this is actually acting in a reduced space. So if you're familiar with the learned ones, you can do it's basically like a model reduction. You can learn to bring down your problem, and then the denoising happened in that smaller space, and then we decode back into the surface. So it works slightly better here. And now the R, this is a coefficient of determination. So having the distribution, now you can actually, as the questions before, you can really compute the distance across a whole distribution. So Wasserstein distances are a popular one. Jensen-Chen divergence, or this is more similar to coefficient of determination. And in this case, 1 would be a perfect match. That's difficult to reach, but this value of almost 0.9 is pretty good, and here it's almost at 9.6. So right here, the 0.6 indicate this actually did also for the other samples that are not shown, do a bad job here. Yeah.
So you're not actually doing the time stepping like in the example before.
Exactly.
So you get the distribution right away as a result of the.
So here we're producing 500 different samples. We're producing, I think even more from the ground truth to have a stable distribution. Then we're comparing the spatial samples with all of the others. Typically, they do a kind of cross match to see estimate the likelihoods of these different samples. So you have to compare on the order of 500 samples for ground truth, and the other one in a kind of mixed way. You try to match the likelihood of the different ones across all of them.
Case, you're actually simulating. You take samples.
Yes,
that's how you get your statistics.
Exactly.
In the model case, you're not doing the time stepping.
Exactly. We take just random samples, and we're treating the ground truth here also as being random. We throw away the time, basically. It's simulated continuously, right? We take in certain intervals. I think the time step was too small. We enlarge it to have some reasonable differences. And we take 500 of those over time.
Yeah.
Then forget they were over time, which also for these distributional metrics does not matter. Right? So you just want to, it is somewhat, it typically has some periodic behavior, and then we would like to basically capture the peaks and the more likely states of the time evolution in the produced samples again. So this did work quite nicely overall, and now also question is that did it pay off? In this case, we actually have a simulator. We can produce these samples, and here you get a really nice speed up, because for these learned models, we can now completely skip this warm-up phase. We can directly produce samples from the developed part. So here you actually really see large speedups, and I think this is not too far from practical applications. There are many we're actually interested in, right? How does the pressure distribution work? Like, you're not interested in these warm-up phases. You want to try for a new car geometry or so, how it behaves in a flow. And if you train a network for the right regime of behavior, you could actually directly sample the different possible answers. And yeah, so the simulator was on a CPU in this case, running the network on a CPU, especially with this latent version, did produce a nice speed up here, especially with this latent state version around 60, and then when you run it on the GPU, you get another factor of 20 here for the network speed up. Of course, you could also then try to port the solver over to the GPU, but right. So this is admittedly a somewhat dangerous comparison, but more the state of the art. Given the solver, this was open. I think this was not open form in this case, but out of the box with the given software, basically you get a nice speed up out of this training process.
How does the resources required for training compared to these resources? So, I mean, you need to train the model. You need to train.
Yes, right. It definitely, this is not simple to train. So the simulations also take several hours. I think the model trained around a week. So it's probably at least 20 simulations you need. So this only pays off if you know you need to run this model often enough that it covers the upfront cost of training the model. Yeah.
But how specific is the learning procedure? So if I change the shape of the profile of the airfoil or some other parameter,
right?
How generic is
generalization? So all these variations are for unseen shapes of the airfoils. And generally, if you want to vary anything later on, that's what you need to vary at training time. So that's our recommendation here typically. So if you train your model, right, in this case, it was a certain actually flow conditions, right? If any parameter is fixed, if you were trained with one geometry, then inputting a new geometry would not give any answer. Here we had several hundred shapes it was trained for, and then the variation, also the one shown here, is one not in the training data. So then if you vary this at training time, you can also later on input new geometries. So this is typically an important step to do here. Yeah, but right, it's no magic here, right? It basically learns from the examples provided, and it can vary the parameters it was trained for, but right, it doesn't magically extract flow knowledge from this. But it can, in this case, actually work with different geometries, for example, or the different surface discretizations. This was handled here, but right, this couldn't do another pipe flow or something, right? This is specifically trained for airfoil dynamics.
Yes, much
better. Okay, I was just asking if you run on parallel GPUs or on single GPU.
I think
maybe it came again. Yeah, question comes several times.
I would need to look it up in the paper, but this was not overly expensive in terms of training. I think it took around a week or one or two regular GPUs. So this is actually a relatively small model.
Okay.
It was not overly. I come to the larger models later on. Yeah, so I do want to mention that in this diffusion process, it is actually interesting to bring in physical priors. So I had this picture on the slides beforehand. And if we have simulators, so far, basically, we really just worked with the data. It was compared to simulations, but we can throw away all of that knowledge, what we had about the dynamics of Navier-Stokes and solvers and numerical methods, just produce data and then train a network with that data. So it's at least an interesting avenue of work to try and re-include that human knowledge into the process. It's actually a debate in machine learning whether it's a good idea or not. Some people say it's not because it's over constraints or could detract from the real things to be learned. In many settings, if you don't overdo it, it seems to be a good idea. And we did try that in the setting of denoising. And basically, we have assume we have a solver here, this P shown here. Could be an Navier-Stokes simulator or some additional constraints, divergence freeness or so. And now the idea is that at training time, or also when you do this denoising, you can run the simulator and provide a gradient to the model at training time to go back to the weights of the network. At inference time, you would go to the state of the flow. But bringing in the physical model in the denoising process to basically improve the validity of the physical samples is an interesting line of work. And one of the main things we noticed while doing this is that there seems to be, in a way, it's almost a contradicting or conflicting goals, basically. So we have this physical accuracy with respect to whatever you impose with the solver, with your constraint. And then we had what was before the main picture, the distribution accuracy. So the spread over the distribution as prescribed by the data. And if you don't pay attention, basically, so this dot at the top here, this PIDM method is a good example. If you basically very strongly focus on the physics constraint, you get a very small, towards the left, residual error. So the physics are fulfilled, but you lose the distribution. So this is basically going back to a mean, unfortunately, mostly, and producing more or less very similar answers, not providing the spread with different answers. And that's a bit also what the line here should indicate. There's like a Pareto front. So you have basically potentially conflicting goals, and you ideally need to lower both at a similar time. And so it's not a huge step, but we found from one, right, so this is one of the recent works, one of the combinations of this actually providing these physics constraints at training time to a model did help. So it did lower this compromise a bit, getting a decent distributional accuracy while getting lower residual accuracy for the physics in this context. And the nice thing about doing this training time is that the model is later on not slower than normal diffusion model. So it still needs to run, in this case, 10 times or so, but you don't need to potentially evaluate costly physics while doing the denoising steps later on. Right. So we do have a bit more of a real world case. So this is now this formation dynamic store. So this is from real world scenario for rotor blades for propellers. Again, we're down to the surface. So this is not a full Navier-Stokes solve, but nonetheless, you can impose a few constraints between the interplay of the different quantities that were predicted here. And again, if you train a model, in this case, it's non-trivial data and it worked really nicely. So we're looking at again, a kind of surface distribution of the flow. And what's compared here in this little table is now, this is a version with physics, and the one next to it is kind of plain learning. This is the flow matching variant, but basically solves the same problem as these diffusion methods before. And they're basically almost the same time. Here, this is basically 60 milliseconds. And if you look at things like here, the first one, the RE value is the physics residual. So in this case, it really paid off a lot to impose this constraint. This is much lower for this variant. And the Wasserstein distance here, this is one of these distribution metrics now for the whole spread of the different answers. Here, interestingly, this variant was actually also better, but they're pretty close together. So in this case, the physics residual helped a lot. It depends on the case. So, right, I don't want to claim that it's always working this well, but depending on what kind of constraints and laws you have, and the scenario and the training data, this can actually make sense. Yeah, nonetheless, as you can see here, so these are really the whole outputs. They are relevant for industry. So, right, for propellers, these are potentially interesting data sets, and they're actually also pretty costly to produce, but they're still fairly low dimensional. So I think an important outlook going ahead in the future will be scaling this up. Now, at least I want to give a bit of an outlook for the high performance direction. This now brings back this architecture question. So the architectures provided so far would not scale well. This requires a bit more work, but especially these transformer variants, which also drive things like ChatGPT and Co. at the moment, they actually turn out to be also really good for any problem, basically, also physics simulations. If you rethink it, it's nothing with, so these sequences that you have for text now don't play a role anymore. Basically, we're just looking more like convolutions at receptive fields within a data set. But nonetheless, these transformers can actually deal with kind of neighborhoods in data, spatial neighborhoods as well. If you set it up a bit differently to the normal ones. And this is one architecture that, from our experience, worked particularly well, this PDE transformer architecture. And actually here we got some great help from the Helmer cluster. These runs would have been, right, we probably would not have been able to do without the GPUs there. So thanks, I should mention here for that. And it really did work up nicely. We were able to run models that could scale up to 512 cubed. This is on the order of, I think, 400 for flow, 400 million degrees of freedom. This is something you cannot easily do with other architectures. It was admittedly not trained on that right from the start. This even would have required scaling up to much larger systems. These were trained, I think, max of 8 GPUs, but also quite a bit more costly than the model I've shown before. But at least for isotropic Turing's cases, they got later on scale this we used to produce samples that were very large. A nice side effect is also it seems to generalize nicely if you set it up that you can work with different input-output channels. But probably a bit more importantly, we're coming back to this probabilistic picture. In the end, it's actually not such a big step. If you set up your architecture correctly, whether you do the deterministic task or the diffusion task, is not a big change. Also with these transformers, we can actually do this denoising. So here's an example with really simple geometry, but we mimic this case of producing just samples over time, treating them as a distribution. This is now a turbulent channel flow of around, I think, 200 by 192 by 128 by 128. So at least 3D with a decent number of samples. And interestingly, because training is a bottleneck, we trained on basically these cropped regions of 48 cubed and then combined multiple of these to produce the final answer. And that means you actually need another network to synchronize these different blocks. But if you do that and then run through these multiple joint blocks, the transformer blocks, basically, you can get globally valid samples that also do match the distributions quite nicely. So here the geometry was not varied, but Reynolds numbers, and this is now distribution across the channel direction for the velocity itself, but for a 3D scenario. So it's just the first test, admittedly, but I think with the right architectures and ongoing work here, this potentially could be used to be scaled up and to provide large-scale answers for probabilistic problems. All right. Oh, yeah.
That's right. So
yes.
Coupling these smaller models is more efficient, resource efficient than just training a model on the full grid.
So the problem here is the training, actually. Even training these 48 cubed regions, it's a fairly large model. This one has, I think, more than 100 million parameters for this theta. And then the memory of the GPUs becomes a bottleneck. So this was trained on, I think, up to eight GPUs, but for one typical training batch, then build these up basically. So training the whole block just would not have fit or would have required, right, in this case, quite a factor of GPUs on top of that. And I think this modularity is potentially also an interesting aspect, actually, because you asked about training time. So if we could pre-train some smaller blocks and reuse them a bit like done here, this could potentially lower the training time a lot, right? So because this required many GPUs, I don't think many people would have these at home. The 80 gigabyte H200 GPUs. So this is definitely non-trivial to train. And pre-training this and then potentially adapting it to new physics, and just train for one specific instance here, I think that would be interesting for making this more general and more usable. And then also can pre-train blocks and combine this basically for other volumes. This could also give flexibility to lower the training cost basically. Yeah, but with that, I want to come to the conclusions. I hope I was able to show that these Gen AI technologies for diffusion models are actually a nice capability, and working with these probabilities is actually non-trivial for classic simulators. This is really, I think, a powerful aspect of deep learning, and nonetheless, our understanding in the form of equations or constraints still seems to improve the results. So it's good to combine both. Nonetheless, despite all these, I think this is a nice closing video. So this is no AI, no neural networks involved here. This is just a classic simulator, in this case, just on one workstation. So if you do it right, you can also deal with very large scale phenomena with, in this case, billions of particles on a huge adaptive grid. and scaling up the networks to these kind of sizes and dealing with the complexity of these phenomena is definitely still an ongoing challenge. But I think there's a lot of interesting work left to be done. If you're interested in diffusion models or the integration of these solvers, we have a website that summarizes these with code examples. And I want to thank the students working on this, Chang Georg, Björn, Li Wei, Benjamin, and Bernhard. And thanks for listening.
Okay, thanks a lot. Are there any questions or points for discussion, doubts, please? Yes.
Thank you very much. It's a nice talk. It was very intriguing that you mentioned the diffusion model has another dimension T, generated iteratively the innovation process. But I was somehow confused that in the turbulence simulation, it looks like we have different time step T, like for physical time step T for the turbulence simulation, and also diffusion time step T, the diffusion process.
Yes, okay.
So we basically use the diffusion process for each time step T of physical time step T, which is the snapshot of simulation, right?
Good, you're asking, right? No, the diffusion time has no physical meaning.
Yeah, so it's a different,
right? It's a different time.
For the diffusion process, we need the diffusion time step T, right? So when we use the diffusion model for the turbulence simulation, we need to repeat the diffusion time step T for the physical time step T of the turbulence simulation.
So the one picture I showed with the animations,
the
series, that really looked at steps over time. That was basically an iterative process for the time stepping. Therefore, every one step of the simulator, learned or not, we do these 100 denoising steps. So it's 100 denoising steps, one time step, 100 denoising second time step, and so on. In the later examples, we forgot about time. There was no time anymore. So the network just dumped in time and produced arbitrary samples with the right probability, approximately at least, right? But it did not know about the time. The time was not an input, physical time.
Okay, yeah, I got it. So do we use the same diffusion model, the shared weight for the physical time step T? So like for the
yes, it is basically just one model,
but that different condition, right?
Yes, it was in this case conditioned on one step, learning to produce a fixed dt in physical time as the next output. You could also provide this as a parameter, right? This generalization, this was pre-trained for a hard time step. If you vary this, you can train models that do varying time steps, but in this case, a model knew about the time in terms of being trained to provide one time step of physical time.
All right, thank you. Thank you very much.
Another one here?
So at this point, you didn't talk much about the physics or differentiable physics that you use for implementing the physics constraints. I was just wondering, looking at your 5-flow especially, why you never touched finite elements.
Okay, yes, differential physics is a very good keyword. I mostly skipped this today. I had another talk yesterday where I talked a lot about this. I thought, in case anyone dares to show up to both, would have been boring to go into too much detail here. But it is a very good keyword and one of the building blocks. So this came into play for the last example with the stall cases. There, it's actually great to have a differential solver, and specifically finite elements for 5-flow. Is just with 5-flow, we looked at very general and flexible combinations of different physics constraints, Lagrangian or grid-based, also with learning, and we just did not get around to implementing a proper FEM solve in there. It would have been a great extension. We had some unstructured. The latest versions have some code for unstructured grids, but we just didn't get to it. We now have a separate solver that on a cooler level has kind of custom optimized operators for deformed grids, so some FEM finite volumes in this case, but that can deal with these kind of multi-block structures and has differentiability on that front in a native PyTorch setting. 5-flow supported PyTorch, JAX, and TensorFlow back then, a couple of years that was widely used, so it tried to be very broad. But that made it difficult also to support all the different simulation types and backends. So yeah.
This new one, it's not just on Navier-Stokes, it's
also Navier-Stokes. Unfortunately, it's also only Navier-Stokes, incompressible flows, piso at least a higher order time stepping method on these multi-block grids, because that's admittedly one of the challenges at the moment. Many classic codes don't necessarily interface well with these derivatives and with deep learning, but I think it's a very valuable avenue for the next generations of codes.
Do you think that code would be easily extendable to compressible flows, or?
Compressible flows should be doable, but it's not straightforward, right? You need to modify the system matrix, and it has preconditionals for the differently shaped elements. I think it's doable, but not trivial. But I can, if you're interested, this is PICT picked code. I can recommend taking a look. Would be an interesting extension, but compressible so far is not yet supported. Yeah.
Maybe that's a related question, but what about the weather?
Yeah.
In the weather forecast, it's exactly what we get. We get a range of temperatures and pressures, and that's what we want.
Right. Yeah.
What would you need to do to produce a weather forecast?
It is happening. You actually have these models. It's not right. We're not dealing with this a lot because for weather you need a lot of expertise about handling the inputs and analyzing them and so on. And in my group, we're mostly focusing on fluid flow. So I actually had a postdoc who knew about this. Then we could do a bit of weather simulations, but since he left, it's been mostly dormant. But if I did actually recently talk to colleagues from weather and climate, and they say weather is basically solved, right? So this Gen AI for weather is done. This will work. This will come, and it's not even so interesting for research. This is clear. There are some first models from Google DeepMind and co. doing this, and first applications really on for short-term forecasting, a few days, the typical weather that you see with trained neural network models. So this is not widely used, but now in production use basically for the forecasting. It seems climate is much tougher. These long time scales, that's still interesting for research, but these short-term weather forecasts are working with these techniques. And right, they actually use what I talked about, these generative AI technologies. Yeah. But right, I didn't have any good examples to show on that front. Things called GenCast is one of the popular papers that does exactly this diffusion modeling for weather forecasting. I think there are a couple of others coming up at the moment.